These growing game trees are from Google DeepMind's multi-million-dollar AI, illustrating how the AI thinks about chess. And these growing game trees are ones that I built from scratch in Python, now playing the classic kids game Connect 4. Both of these trees represent the inner workings of AlphaZero, Google's AI algorithm that achieved superhuman performance in chess and Go, and that I trained to play Connect 4. AlphaZero was revolutionary not only because it achieved incredible performance in all these games, but also because it had a completely different style than previous game-playing AIs. Former world chess champion Garry Kasparov said that AlphaZero was kind of like the opposite of traditional chess engines, and that it was exceptionally creative. This creativity emerged because AlphaZero was created in a very different way than traditional game-playing AIs. It was taught entirely through self-play, only learning strategies by playing games against itself without any handcrafted human strategies put into the AI at all. This is what the zero in AlphaZero stands for, starting with zero knowledge and learning from there. And for me, this is the absolutely most paradoxical thing about AlphaZero. Because there are no complicated human strategies put in there, it's actually a really simple learning algorithm running under the hood. In a recent seminar in 2026, David Silver, who was the lead author of AlphaZero, put 3 simple bullet points on a slide and proclaimed it was just these 3 steps and literally nothing else. In other words, what AlphaZero learned was completely superhuman and extraordinary, but how it learns is something that anybody can understand. This is exactly my goal in this video series, to really explain exactly how the AlphaZero algorithm works and how simple it really is under the hood. And to help with this, I'm going to explain everything using this Connect 4 example that I showed you earlier. I've released this as an online interactive notebook. You can run it in your browser, link in the description, and it has buttons to let you step through all the individual steps of the algorithm and really see what's going on. Now, I've taught about AlphaZero before in university-level courses, but I've always done it at the blackboard in a sort of abstract, made-up way, and I've never had this tool of actually showing you an algorithm that really works and really plays a game. This is the tool that I've always wanted to show students, and I finally took the time to make it. You don't need to know any coding to run this, it's all interactive and with buttons, but if you want to look at the code, you can click into it and see all the Python code that is there. Lastly, I've structured my videos around Connect 4, but I know some people are hung up on the fact that Connect 4 is technically a solved game. And so I've actually made it so you can change the rules of the game. If you make the board a little bit bigger, where the board is 8 columns wide, or even 9 columns wide, then the game is no longer solved, and computers are no longer powerful enough to figure this out. Either way, the point of this video series is to understand the inside workings of the AlphaZero algorithm using Connect 4 as an example, not necessarily to make the best possible Connect 4 AI. And like the classic first-generation Pokemon Charizard, this video series comes to you in 3 parts, each building on the previous one to level up the AI and develop the key ideas of AlphaZero step by step. Today's video is the first in the series, and it's about the UCB algorithm. To me, this algorithm is the heart of AlphaZero, and it runs literally tens of thousands of times every time AlphaZero makes a single move. This core algorithm is in charge of deciding which moves AlphaZero will think about next, and it has to balance new, tricky, unconventional moves with sort of the classic default moves that you would first think to play. I really believe that it's this balancing of really unconventional moves with kind of the classic moves you would expect that makes AlphaZero so creative. It's able to find weird moves that you wouldn't think work at first, but turn out to do actually work. And by the end of this video, we're going to have an extremely simple algorithm that works just using the UCB algorithm and nothing else, but that you can still play against and have a little bit of fun, and you can see why just that on its own will not be enough. In the second video, we're going to evolve from UCB to something called Monte Carlo Tree Search, which is the secret to how AlphaZero manages these exponentially growing game trees and how does it keep track of them without making them too large. This is how AlphaZero is able to go really, really deep on some moves, but sort of discard moves that aren't working out almost immediately without wasting room in the game tree. And finally, we're going to unlock the power of convolutional neural networks to unleash the full power of modern machine learning that makes AlphaZero so powerful. I've really tried hard here to spend some effort to really look inside of the neural networks and see what are they actually doing in these Connect 4 positions, and how are they learning the skills that we need in Connect 4. So if you're excited to learn about this full journey of AlphaZero with me, make sure you subscribe so you don't miss these future videos. But just as the mighty Charizard starts his life out as a humble Charmander, we too will start with the humble UCB algorithm. This algorithm can be thought of as the optimal A/B testing algorithm. What it does is select options to try out in an uncertain environment where you don't know what is good or what is bad. For us, that means choosing what to play in Connect 4. So you can think of, we have a Connect 4 position like this one shown here, and we have several options of what move we would like to play, and we don't know which moves are good or bad. The UCB algorithm is in charge of deciding which of these moves to try out, to learn more about, so we can figure out which one is the best. This algorithm is good not just for board games, but anytime you have this sort of decision-making process where you have multiple different things and you don't know which one is the best. There's a really nice example I like from the company Netflix, where they have a blog post made by their data science team many years ago now that talks about how they use the UCB algorithm to choose out the best thumbnails. And what they do is they make a lot of these different thumbnails, and the UCB algorithm decides which one of them to show to viewers to gain data about which ones are working and which ones aren't. So it's a really nice algorithm, and it works in a lot of important situations. Now, the fundamental philosophy of this thing is completely different than traditional game-playing AIs, and I want to talk a little bit about this to make sure there's no confusion between what we're doing here and how other algorithms work. Now, the old classical way of doing AIs is to sort of think about combinatorics and finding the best move. So the old philosophy, you could say, is about this. There is some best move out there, and we just have to find it efficiently. And this uses techniques from search and graphs to find the best algorithm in the best possible way, to prune the trees, to cut down the search space and that kind of thing. Or maybe if you're very clever, you'll say there is some best answer and I can't find it, but I can find an answer that is within, a factor of 2 of the best possible answer. So that's the old classical way of thinking. And this kind of leads into these things of saying, oh, we've solved the game. We found the best possible move in all situations and things like that. The classic Deep Blue that beat Garry Kasparov many years ago ran this kind of search, right? They had human crafted features that would help the AI cut down the tree and say, don't worry about searching for these moves, search these ones first, and let's search the whole game tree as fast as we can to find really good moves. Now, what we're doing in AlphaZero is completely different. And I think this is the new kind of machine learning way of thinking about things. We're going to completely throw out this idea that there is a best answer, and we're going to think about things in terms of uncertainty. We're going to really embrace the uncertainty. So the way I think about it is like this. We will never, ever be 100% certain what is the best possible move. We are just going to give up this notion of the best move completely, and we're going to think in terms of evidence and knowledge. So we can gain knowledge about which moves are good or bad. We'll never be 100% sure, but we can spend our resources to gain more evidence and be more sure about which one is the best. And the more time we spend thinking, the more evidence we can gather, and the more we can be, confident that one move is better than the other, even if we're not right 100% of the time. This is kind of a probability, statistics, machine learning way of thinking about things that's very different than the classical way of doing things. So you really have to embrace this way of thinking to do AlphaZero. And the advantage is we can run this on a much bigger set of games. So even games that are too big, if the search space is too large to do the combinatorics approach, the fundamental philosophy of thinking in terms of uncertainty should still work. A really nice example of this way of thinking is the hello world of machine learning, the MNIST digit recognition task. In this task, you're given a picture of a digit. I have it drawn over here in yellow and blue, and we have to recognize what digit is this. Now, the thing about recognizing digits that are drawn on a piece of paper is they're fundamentally, you will never ever know the actual right answer. There is a training set where we have been given some examples that have been labeled, but even that will have some mistakes. So it's not really about finding out what is the true answer to what this digit is. It's about answering the question, what is this digit likely to be? And for this, I picked a particular one here that is kind of ugly, and it's not clear at all what digit this person meant to draw. It looks, it looks a little bit like a squiggle, but the AI algorithm thinks that this is probably a 9. And indeed, if you added the top little bit to it, if you were just added that little loop around the top, then it would look a lot like a 9. So the AI algorithm is saying, look, we don't know for sure. Could be a 9, could be something else, but the most likely thing we think it is a 9. And that is also how our Connect 4 algorithm is going to work. It's going to look at positions and it's just going to gain evidence and say, look, I think based on the experiments I've done that this one is the best, and I'm not sure. But here is my layout of the things I've tried and how much evidence I've gathered. And the key idea that AlphaZero is going to use is something called random rollouts. So what is a rollout? You should think of it as a random experiment that we do to test whether or not a board position is good or bad. And what we do is we just fill in moves randomly. We decide what would happen if both players played completely at random, and we just simulate that happening one time, and we see who won the game. Did player 1 win or did player 2 win? And the idea is if player 1 wins the game, then that experiment is some evidence that this position is actually more favorable for player 1. And if player 2 wins the game at the end of this random turn taking, then it's evidence that this position is more favorable for player 2. The first time I heard about this, I was like, this is totally nuts. Like, how on earth can we make this work? This is not at all how people play games. They don't play randomly. They play according to strategy. So how is it that playing randomly is going to tell us anything about it? And again, I think you should think of it as comparing things. And so I've come up with this example. In this board position, what would be better? Playing in the second column or playing in the 7th column? And again, the classical way of thinking is to say, oh, if I play in the second, then where will blue play? And so on and so on. We're the red player here, by the way. And you might actually use some strategy to conclude that if you play in the 7th column, you will immediately lose the game. So we know for sure that the second column is the right answer, but let's see how the random rollouts way of thinking would reveal that answer. So here's what we do. We run an experiment where we run a random rollout from each move. So we say, If we played in the second column, I've indicated the most recent move with this open red circle, then what would happen? And we play random moves, all the random moves come in. I've drawn them with this kind of faded out color to see, so you can see the random moves, but they're not really on the board yet. And you can see that in this situation, red eventually won by getting a nice diagonal across there. So they've connected 4 and they won in this particular random rollout. On the other hand, if we played in the 7th column, then we play a bunch of random moves, and we see that in this scenario, blue happened to win the game. They got connect 4 along the bottom over there. And of course, they didn't get it right away by using the strategy that a good player would get, but in the random rollout, it turned out that blue won the game. And so based on these 2 simple experiments, 1 random rollout from each position, we can kind of conclude that, we have evidence that column 2 is a better play. Now, of course, this is extremely weak evidence. We've only done 1 random rollout from each, and the random rollouts aren't perfect, and they're also random, so just having one single sample where column 2 was better and one single sample where column 7 was worse doesn't actually tell you which is better, but it is evidence. And this is the whole point of this way of thinking, is that we can get really weak evidence and just amplify it by repeating the process over and over again. And eventually, when we get to neural networks, we're going to have not just purely random rollouts, but random rollouts that are guided by the neural network. And we'll see that it's even better when we get there. So this is the main idea, but we just need to amplify it by repeating the experiment many times. And for that, we're going to go to the actual Python program. I really hope you'll follow me along by clicking the link in the description, and you can play along and see how this works. Okay, so we're here in the interactive Python notebook. This is running in something called Marimo, which lets you add buttons and things like that to Python. And over here, you can see the board position we were talking about before. We have this situation over here, and we're comparing column 2 and column 7. In this thing, columns are called actions. This is a standard terminology from reinforcement learning, is that when your AI is doing something, that thing is called an action. Because Python starts at 0, column 1 is actually called action 0, column 2 is actually called action 1, and action 6 is the lastmost column. And we have these buttons over here to try these different things. So if I press this button, we will run one of those random rollouts that we were talking about before. So for example, to try the second column, that would be try column A1. And so that will try A1, and there you go. It tried column A1 just like before. We have this move that we did, and then the rest of it is sort of faded out to show that it is the random rollout. It is not part of what is going on. And over here, we've recorded the result. So it says the result was -1, and I believe there should be maybe somewhere that tells you what the things are. Oh yeah, over here in the very corner, it says P1 is +1. If player 1 wins, that's +1. If player 2 wins, that's -1. If it's a tie, that's a 0. And because we got a -1, that means player 2 won. So the blue player actually won. And now let me see on the board here, where did the blue player actually win? There it is, right there. The blue player got 4 in a row over here. So this is evidence that column 2 was a bad move. We played in column 2, and the blue player won. That's bad for us. We want to compare this to playing in the last column. So we say try A6. We'll press this button right here, try A6, and let me press it. Okay, here we go. Wow, okay, we tried A6, and look at this. This time the blue player won again, so it's another -1. And of course, anybody who has taken a statistics class knows you need a larger sample size. So doing it one time for each really doesn't tell you a lot. What you really should do is do it many times. So let me try pressing it, let's say 5 times on each. So I've done 5 times on column trying action A1, and let me do 5 times also for the last one. Okay, and you can see I've done them 5 times each. This x-axis over here is the number of times I've done them. So each bar is telling me the height. The height of each bar is telling me how many times I've done it. I've done them both 5 times. And the number over here tells me the average. So when I did try A1 column 2, trying action A1, I got an average of 0.2 over my 5 tries. And 0.2 on average means that player 1 is winning more often than player 2. That's because player 1 is the positive numbers and player 2 is the negative numbers. In fact, the nice interpretation is that this is saying that the amount of times that player 1 won is 20% more often than the amount of times player 2 won. So player 1 is winning 20% more than player 2. On the other hand, in column A7, it's the reverse. It's a negative 0.2. So that means player 2 is winning more often and is winning 20% more than player 1. You might not be convinced with only 5 rollouts for each. You might say, we need even more evidence. So you say, okay, let's do it 5 more times for each. So 1, 2, 3, 4, 5 more times. Now we're up to 10 simulations from action A1. And let's do 10 simulations from over here for action A6. Okay, and now the averages have changed again. It turns out the average in column A1 was exactly 0. There were an equal number of things where player 1 won and an equal number where player 2 won. They've both won an equal amount of time. Player 1 and player 2 seem even based on our 10 simulations. On the other hand, playing in column action A6 in the very last column seems really bad for player 1. Player 2 is beating player 1 40% of the time more than player 1 wins. So this is evidence that between these two choices, this choice is better than this choice. And you could start to get a little bit more, do some more statistics and say, do we have enough of a sample size and that kind of thing? We are going to get into that kind of question. The elephant in the room is, what are these delicious pita breads sitting on the bottom over here? NaN stands for not a number. And this is what's going on. We have not tried any of the other actions at all. So, maybe we should also try these other actions. Let's do each of them 10 times. Action A0. 1, 2, 3, 4, 5, 6, 1, 9, 5, 6, 7, 8, 9, 10. I've tried action A0. Let's do all of them 10 times until all our columns are even. Okay. Trying action A4. So trying this a bunch of times. And trying action A5. Okay, so now I have done each of these actions 10 times each. Now I'm ready to ask the question, not only which is better between A1 and A6, but which is better overall? What is the best move based on my evidence that I can play? And it's the one with the highest average is one way to do it. So as I'm seeing a 0.3, so that is kind of saying that action 4 seems like it would be the best. And fundamentally, what we're going to run into is that when there are a lot of different actions and we need to run a lot of different rollouts to figure out which ones are good and bad, there is a fundamental waste of energy here on the bad moves. So for example, action A6, the farmost column, is going really badly. Maybe we should just stop trying that one. So instead of doing them all equally, doing them 10 times each, maybe we should focus our attention in on the better ones. And this is fundamentally what the UCB algorithm is going to do. It's going to say, for a given budget of rollouts, let's say we have 100 simulations that we can run. We have enough time in our planning that we can have enough time to run 100 random rollouts. How should we spread out the random rollouts? And what you should understand is that doing it all evenly like we have here, with all of them tried an equal number of times, is not a good enough strategy. So for this very simple AI that we're going to do today, it wouldn't be much better or worse doing it this way. But as we make it more and more complicated, it really is critically important that we eliminate the bad moves and don't waste our random rollouts on the bad moves. So let's start over here. I'm going to reset this thing, but let me reset this from the beginning and let me try a different algorithm. So instead of doing them all equally, let me try something else entirely. Let me try to eliminate those moves that are not promising and not waste my time thinking about those. So I guess to start with, they're all not a number. I have nothing to go on. Maybe I'll try each of them once to start with. So trying them each of them once to start with. And now I'm going to aggressively eliminate moves. So look at this. Action 1 and action 2 and action 3 and action 6, we lost. Those were all bad moves. The other player won. So I'm going to stick to actions 0, 4, and 5. And let's try those. So action 0, I'll try that again. Action 4 and action 5, I'll try those again. And now of those, look at this. Action 0, I won again. Action 0, we have an unbeaten record. So maybe I'll try just action 0 one more time. Okay, we're still unbeaten. Let's do action 0 again. Okay, now action 0 has a 0.5. We won half the games. We also won half the games in action 5. So action 0 and action 5 are both pretty good. Let's try both of those. Action 0 and action 5. And look at this. Action 0 is the best one. So let me try keep doing action 0, action 0, action 0, action 0, always 0, always 0, always 0. This algorithm is called the greedy algorithm. You say which one is doing the best so far. Let's keep doing that one over and over again. And always 0. So you see, even though it's starting to come down, action 0 is still the best one over here. And this bar chart is showing us that we've spent almost all our effort doing action 0. And we could keep going. But I hope you will recognize that this is a bad algorithm. Doing the greedy algorithm in this case is going to lead us astray. And that is because we were too quick to discard some of the earlier moves. So moves like action 1 and action 4, which are these two columns over here, we know from our experience playing Connect 4 that these are pretty good moves, and we probably should be playing one of those two. In fact, we have to play one of those two. But we threw those out because they sort of got unlucky near the beginning. So we can't be so aggressive in throwing out our moves near the beginning, like we were just now with the greedy algorithm. And we also can't be so egalitarian to try everything evenly. We have to do something in between. So let me reset this problem and let's see what the actual best answer is. So we've seen egalitarian, trying them all equally. That is not good. That is wasting too much time on the bad moves. We've seen greedy, trying only the move that seems the best so far. That is also not good because it will eliminate good moves too early. The optimal thing in between these two things. The Goldilocks algorithm is the thing I have mentioned many times now, the UCB algorithm. And if you press this button over here, automatically choose action with UCB, it will run the UCB algorithm over and over and over again. Now, I'm going to save some time here by just putting in a large number, let's say 1,000 times, for the number of times to run this. And when I press this button, it will sequentially run it over and over and over again. So instead of me sitting there and pressing the button 1,000 times, I press the button once. And let's see what the results are. Which moves will the UCB algorithm try? And here we go. Okay, so the UCB algorithm ran, and it looked like action A1 was run the most often, and second was action A4. So pretty quickly, the algorithm sort of eliminated action A6 playing in the far column. We know that's a bad move. It eliminated that as a possibility because it was quite bad. Negative 0.87, player 2 was winning a lot. It also sort of eliminated action A0, didn't play that many times, and it spent almost all of its effort, 480 out of 1,000, out of a budget of 1,000, playing in action A1. So it kind of thinks action A1 is the best. So the UCB algorithm, that is what it does. It does a Goldilocks in between being pure egalitarian and being pure greedy on where to spend our random rollouts. And at this point in the video, I could just tell you the formula. In fact, if we scroll down a little bit over here, you'll see a different representation of the same exact thing we've done before of the root state we started in and the different states we could try, and this little indication of, we're doing these rollout simulations to see what happened. And we have the number of times we've done each one listed over here. And we have the averages listed over here, the same exact information that was in that bar chart. And if we click on one extra button down here, show UCB scores, then it will add some information, and the UCB algorithm can be very simply explained with a single mathematical formula telling you what this formula is and how it is used. And in fact, that will be later in the video. If you're impatient and you just want to see what's the goddamn formula, skip ahead to this timestamp and I'll tell you the formula. But if you'll indulge me, there is one more thing I want to do to show you, to get a sense of this Goldilocks decision, of this tension between trying new things and trying the most promising thing. And so I have made a little mini game. It's a little fishing mini game, and it's called the Fishing Bandits minigame. And that's because this kind of problem is called a bandit problem. Now, this name of bandit problem I find extremely weird, and so I made a quick little slide here explaining where it comes from. It all starts with this slang term for a one-armed bandit, which is a slot machine. So a slot machine takes your money and it has one arm, therefore people call it a one-armed bandit. Well, then what is a multi-armed bandit? Well, that would be a bunch of slot machines all in a row, like you see here in this little cartoon, an octopus playing lots of different slot machines. So that's a multi-armed bandit. And a bandit problem is short for the multi-armed bandit determination problem, which is to figure out which of these slot machines, in a big bank of slot machines, which of them has the best payouts. So you have a bunch of different slot machines. Some of them take your money a lot. Some of them maybe are actually profitable. But how can you figure out which is which? The only way is to play them and test them out and see which one is the best. And I hope you'll see that this position that we've been working on in Connect 4 is exactly this kind of thing. You can think of each of these different actions as a different arm you pull. And when you pull the arms, you gain information about if it's a good move or a bad move. The only way to learn is by playing. Another example is the example we saw from Netflix, where they had all these different thumbnails and they were trying to find out which one did viewers respond to the best. So they were trying them out and seeing which one is the best. That is a bandit problem. And finally, this fishing minigame is also a bandit problem. So in this bandit problem, there are 4 options. This is one of the reasons this is a little bit easier to learn from than the Connect 4 example, is because there are only 4 options: Lake A, Lake B, Lake C, or Lake D. And it's a little bit more intuitive to learn with just 4 options instead of 7. The other thing we have is we have a budget of 40 turns. So this would be like having a budget of 40 rollouts. And the rules are simple. We are on a 40-day long fishing trip, and every single day we have to pick which lake we want to go fishing at. We can choose any one of these 4 lakes, and our goal is to catch as many fish as possible. Now, the thing that is unknown to us is which lake has the most fish. So every single lake, when you go to it, you will collect some number of fish on your fishing trip, and our job is to collect the most number of fish total on our 40-day fishing trip by finding out which lake is the best and going to that lake as many times as we can. But here is the tension: is should we try all the lakes a lot, or should we narrow in really quickly on which lake we think is the best? How do we balance these two things? And I'm going to use this random seed 1605. If you want to play along with me, you can type in this seed up here and click use fixed seed, and you'll have the exact same randomness as me. So you can try the game and see, will you collect more fish than me? And at the end, we're going to compare to the UCB algorithm and see, did we collect even more fish than the UCB algorithm? So I highly encourage you, if you want to try this out and really get a sense of what it's like to make these choices, pause the video and try to collect as many fish as you can by using random seed 1605. So the starting move is probably going to be to visit each lake once. Okay, so I caught 13 fish in Lake A, 13 in Lake B, 14 in Lake C, and only 5 fish in Lake D. And now my job is to figure out which ones to try again. So I'm going to try definitely Lake C again. That's the best one. Okay, that's down to 9. So maybe Lake B is now a good choice. Let me try Lake A again as well. Okay, and now we are already in a good tension-filled moment here, where we've tried Lake A twice. We've got 14. So Lake A seems like it's the best lake. That's the average of the number of fish we caught. So I guess if we go down here, we can see we caught 15 and 13 fish at Lake A, which is why the average is 14. And in Lake D, we only went there one time, and we only caught 5 fish. And now the question is, should we do Lake A again? Should we keep going to Lake A because it seems quite good? Or should we go back to Lake D and get like more information? Okay, and to help us do this, I've drawn a little plot here. So this plot shows the averages as little lines. And so you see Lake D is all the way down here, is the worst one, and Lake A is the best one that has the highest average at 14. And so this is just another way to represent the information. But the fun thing we can do here is this button, Show Bell Curve. And now we get a sense of not just the average, but how uncertain we are about the average based on our sample size. So because we've only done Lake D one time, the curve for Lake D, our uncertainty is very wide. We don't know, we've only gotten 5, but we've only tried it one time. So it could be that, there's a lot of fish in Lake D and we just got unlucky the first day. On the other hand, we've tried Lake A more often, so it's a little bit more narrow. Although in this case, I think we've only done it We've only done it 2 times, so it's not super narrow. The point of this is that these bell curves, they come from the central limit theorem, which tells us that in the long run, the averages will be this bell curve shape around the true average. So the true average is what we really care about, and we have limited information about it based on our sample size, and this bell curve shape is capturing that uncertainty. When we look at this, we can see not just is the average of D compared to the average of A, but we can compare this whole bell curve to the average. And we can see that actually the chance of Lake D being above Lake A right now is very, very small. So actually Lake A still seems pretty promising. So let me try Lake A a couple more times. Lake A. Okay, so Lake A, the average went down and it got more narrow because we tried it one more time. I guess we only caught 3 fish that day. You see, Lake A had a bad day. So now what should we try? Well, I guess Lake B is the obvious choice here. Lake B here in blue is looking pretty good. Lake B went down a bit as well, but Lake B I still think is the best. Okay, so now Lake B and Lake A, they both have extremely similar averages. The averages are almost the same, but Lake A is a wider curve. And that's because we've gone to Lake A less often. So Lake A, we've only gone to 3 times, and so we have more uncertainty. And therefore, we should try Lake A. That has a chance of getting more fish. This kind of idea is called optimism in the face of uncertainty. If you're not sure what's going on, it could be that you're missing out on some really good gains from Lake A over here, and so you should try it out. And that's what we're going to do. Let's try Lake A. Okay, Lake A. Lake A is still very good. Lake A is doing great. So Lake A is going quite well, and we're getting a lot of fish from Lake A, and the bell curve is narrowing. And now if you look carefully, you'll see that these other lakes, like Lake D, even though it's quite a bit worse, because we're so much more uncertain about it, the tails over here, like Lake D, even though Lake A is the best, Lake A sort of has the least chance of getting like 15 fish in a day. So actually, I think we're going to go back and let's try some of these other lakes. Let's try Lake D one more time. Lake D moved up to 10. Lake C moved up to, Lake C moved down. Okay, so it looks like Lake D is still doing quite good here in terms of uncertainty. We're still very uncertain about Lake D, so Lake D could be the good one. Let's try Lake D some more. Oh, okay, Lake D moved up. And now we're really thinking Lake D is the best. So even though Lake D had a horrible average, the uncertainty means that maybe it was the best choice. Okay, and now they're all kind of looking similar. To break the tie, I'm going to finally show you this UCB. I'm going to select this button called Show UCB. And what this does is it takes each of these bell curves and it draws a line about halfway into the bell curve. So this is sometimes called the upper confidence bound, or the UCB. The upper confidence bound is the line in the bell curve that captures a certain percent of the volume above it. In this case, I think I did 90%. So 10% of each bell curve is above this UCB. And we can see the different UCB values drawn over here in these dotted lines. And it seems like the UCB value for A, halfway through this red bell curve, seems to be the best one. Okay, and we can check up here. So the UCB for A is 13.29, which we got by taking the average and adding on a little bit for the uncertainty. And that seems to be the highest one. So the UCB algorithm says, calculate these UCB scores based on cutting into these bell curves, and then pick the one with the highest value. So a very simple algorithm in the end that balances the uncertainty about each value based on the sample size with the actual average. Okay, so let's do Lake A here that has the highest UCB. 13, it's still the highest, 13.37. Now it's down to 12.52. So, and Lake D is 12.63. So this is a situation where Lake A has a higher average, but because Lake D has more uncertainty with a lower N, the UCB value is bigger. And we should pick Lake D in this case if we're following the UCB algorithm. Okay, and we proceed like this. Okay, wait, Lake B, I'm missing out on Lake B. 12 point, okay, now back to Lake D over here. And so you can see how this thing is going. We're narrowing them down over time, and we're doing this balance of uncertainty and goodness. This is the UCB algorithm. How many turns do I have left here? 14 turns, almost done my fishing trip. Let's do this UCB algorithm by choosing the best UCB button each time. 11.3, 11.08, 10.5. And so in the end, I'm spending a lot of time here because these lakes are all pretty similar. Okay, now we're on Lake B is the best lake. Wow, Lake B going on a tear. Okay. In the end, we did a lot of flip-flopping back and forth. We tried Lake A bunch. We tried Lake D a bunch. But in the end, it turned out that the UCB algorithm led us to Lake B for the thing we were trying the most at the end. And indeed, revealed at the end of the game was that the best lake was Lake B. So we eventually figured it out. If we had eliminated Lake B too early, then we would have missed out on all those tasty, tasty fish. This tells us that the best lake advantage was 2.15. On average, Lake B actually had 2 extra fish, 2.15 extra fish every time you visit it. So Lake B is the best. And we caught 370 fish so far. The UCB score, if we had done UCB the entire time, by some crazy coincidence, also got 370 fish exactly. And the choices it made, it went 13, 17, 3, and 7. Hey, that's exactly what we did. We ended up doing exactly what the UCB algorithm did. That is a weird coincidence. I do wonder what people did. If you tried it beforehand, before you saw this, put your score in the comments below. And I've run this minigame in a 4th year undergrad math class many times, and nobody has ever beaten the UCB algorithm on their first run through. So very nice algorithm that does a really simple job of balancing exploring with exploiting the one that is the best so far. Okay, and now we're finally ready to see the equation that drives this UCB algorithm that is used in AlphaZero. The UCB algorithm is extremely simple. We just compute this score called the UCB score for each possible action we can take. And so here I've done it for A, thinking of Lake A as what we have been doing. And this formula, you can think of it as coming from the bell curve shape. So the average is the center of the bell curve. That's the average of the results we've seen so far. But we add on this optimism bonus. And the optimism bonus is related to the width of the bell curve. So the wider the bell curve is, the more we add on. By the central limit theorem, the width of that bell curve is proportional to 1 over square root of n. And so the number of times we have tried a certain action is entering into the UCB score with this 1 over square root of n. And so the more we've tried it, the less we add on. If we're very uncertain about something because we haven't tried it much, then we add on a big score. And again, I think you should think of it as the width of this bell curve. The wider it is, the more we are willing to try a certain thing because we're uncertain about it. Like I said before, some people call this the optimism bonus. And so if we're uncertain, we're saying, okay, we don't know about this action. It could end up being a good action. So let's add on what we think could happen optimistically. And so that is another way to think about this thing. You might also notice there is this term C, this constant C. And this constant C tells you how optimistic you are trying to be. If C is very large, you're saying I'm going to be very optimistic. If C was 0, that would be back to the greedy algorithm of always choosing the best average. And by doing the right sized value of C, you're doing the right balance of exploring and exploiting. So that choosing the C value can be very important. So the UCB algorithm, all it does is it calculates this value for every single action, the average plus this optimism bonus that depends on the number of times you've tried each arm. And then we finally just choose the action with the largest UCB value. So whichever one had the largest value, that's the one we go with. I'll end now with a mathematical fact, and this is the reason some people say the UCB algorithm is in some sense optimal, which is if you choose a particular c value of square root of 2 times the square root of ln of t. What is t? Well, let me tell you what t is. T is the total number of times you have tried all the actions you've tried so far. So in this setup, the c value is actually growing as you play longer and longer. So after you've tried 100 actions, then the c value will be one thing, and after you've tried 1,000 actions, the c value will be a little bit larger. And what this means is over time, the longer you play, the more optimistic you are about arms that are bad. And because this is going to infinity, because c is getting larger and larger and larger as you play, eventually you'll play every single arm sort of an infinite number of times. And by doing it this way, you are ensuring that you never leave any arm fully behind. You'll eventually come back and revisit every single arm. You'll never fully eliminate an arm. You'll always come back and try it again at least once. And if you choose the UCB value this way, there's a beautiful paper from 2002 that says that when you choose the UCB algorithm with this growing optimism constant, then what will happen is you will do a really good job of not playing arms that are bad too often. And so the number of times you will play some arm, if it's a suboptimal arm, is bounded by this constant that depends on how bad that arm is. So if that arm has a true average that is less than the optimal average, then you will play it based on the square of that difference. And it grows with the log of t. So it's growing very slowly, logarithmically, and that is why the UCB algorithm is quite good, because it only plays the bad arms sort of logarithmically in the total number of times. You spend almost all your time playing the best arm, and you only spend a logarithmic amount of time playing arms that are not as good. And this is optimal because there is a different argument from many years ago that says that any algorithm whatsoever must do at least the logarithm. You cannot beat this logarithm. And so the UCB algorithm is optimal up to constants. It achieves this logarithmic growth in the number of times you play bad arms, and therefore it is optimal up to constants. Okay, and finally, now that you've understood the UCB algorithm, you can play against an AI that only uses the UCB algorithm. So what it does is it has a little budget for rollouts set by this slider, and right now it's set to 1,000 rollouts per move. And every time you play a move, it takes the position that you give it. So if I play in the middle, it thinks about all the possible things it could do starting from the middle, and it tries rollouts using the UCB algorithm, and then it plays whichever move it determined was the best at the end of its 1,000 rollouts. So in this situation, it tried the middle move, action 3, the most often. It tried action A0 the least often. You see that in action A0, player 1 kept winning a lot more than player 2, and so it didn't try that one as often, whereas action in the middle was the most promising for player 2, having the smallest number over there. And you can keep playing it from there. So, it's a fun little AI. It should be quite easy to beat. And that is because it can never look more than one move ahead. It's doing these random rollouts from one move ahead. In the next video, we're going to add on to this. We're going to use the same UCB algorithm to build up these big, beautiful trees using something called Monte Carlo Tree Search. And Monte Carlo Tree Search is essentially the UCB algorithm, but letting it go deeper into the tree and sort of building the tree up by using the UCB algorithm as a starting point. So that is why it's so important to know the UCB algorithm. It's used in the next evolution to build up the tree and decide good moves many layers down. And I've even included a link where you can play against the Monte Carlo Tree Search AI as well. So if you want to try, you should be able to easily beat this UCB AI, and then you can try playing against the Monte Carlo Tree Search AI, which is a little bit tougher. So I hope you liked that video. I do have 2 more planned that are in the works. The notebooks are almost ready to go. Make sure you subscribe so you don't miss that, and hopefully I'll see you in the next one.